Black holes. These celestial objects are shrouded in darkness, holding secrets that have captivated scientists and stargazers alike for centuries. Imagine a place in space where gravity is so strong that nothing, not even light, can escape its grasp. These cosmic entities are not merely figments of science fiction, but very real objects that populate our universe. They are the remnants of massive stars that have collapsed under their own gravity, creating regions of space-time so dense that they warp the very fabric of reality. But what exactly are black holes? How do they form? And what happens when something falls into one? Join me on this cosmic journey as we delve into the heart of these enigmatic objects. Black holes are born from the death throes of massive stars, those cosmic giants that burn bright but live short lives. When a star much larger than our sun exhausts its nuclear fuel, it can no longer support itself against the relentless pull of gravity. The star's core collapses inward, imploding in a spectacular supernova explosion. This implosion compresses the core to unimaginable densities, creating a region where gravity becomes infinitely strong. This point of infinite density is known as a singularity, the heart of a black hole. Surrounding the singularity is the event horizon, a boundary in space-time beyond which nothing, not even light, can escape. Smaller stars like our sun will eventually shed their outer layers, forming planetary nebulae and leaving behind dense remnants called white dwarfs. Black holes can also form through the direct collapse of massive clouds of gas and dust. Imagine a vast cosmic drain, a point of no return where the pull of gravity is so strong that nothing, not even light, can escape its clutches. This is the event horizon, the defining feature of a black hole. The event horizon is not a physical boundary, but rather a region in spacetime where the curvature caused by the black hole's immense gravity becomes extreme. Once something crosses the event horizon, it is destined to fall into the singularity at the heart of the black hole. Think of it this way. Imagine a ball rolling on a rubber sheet. The ball represents an object in spacetime, and the rubber sheet represents the fabric of spacetime itself. Now place a heavy object like a bowling ball on the sheet. The event horizon is like the point on the sheet where the slope becomes so steep that the ball can no longer roll back out. At the heart of every black hole lies a singularity, a point of infinite density and zero volume. It's here that the known laws of physics break down, and our current understanding of the universe crumbles. Imagine squeezing all the matter in a star, or even an entire galaxy, into an infinitesimally small point. The singularity is often described as a tear in the fabric of spacetime, a point where our current theories of physics simply cannot describe what is happening. Some theories suggest that the singularity might not be a point at all, but rather a ring or a loop, while others propose that it might be a gateway to other universes or dimensions. However, these ideas remain highly speculative, and the true nature of the singularity remains one of the biggest unsolved mysteries in modern physics. Section 5. Black hole. Anatomy: dissecting the cosmic void. Black holes are often depicted as simple, featureless spheres of darkness, but their anatomy is a bit more complex. While we can't see them directly, we can visualize their structure based on our understanding of gravity and spacetime. At the heart of a black hole lies the singularity, a point of infinite density where the laws of physics break down. Surrounding the singularity is the event horizon, the point of no return beyond which nothing can escape the black hole's gravitational pull. Some black holes are surrounded by a swirling disk of superheated gas and dust called an accretion disk. This disk forms as material is pulled towards the black hole, spiraling inward like water going down a drain. As the material in the accretion disk spirals inward, it heats up due to friction and gravitational forces, emitting intense radiation across the electromagnetic spectrum. In addition to accretion disks, some black holes also have jets of high-energy particles that are ejected from the poles of the black hole. Section 6. Hawking radiation, the evaporation of eternity. Black holes are often thought of as inescapable cosmic prisons, but even these gravitational behemoths might not be entirely eternal. In the 1970s, physicist Stephen Hawking proposed that black holes could actually slowly evaporate over time through a process now known as Hawking radiation. This evaporation arises from the strange world of quantum mechanics, which governs the behavior of particles at the smallest scales. According to quantum theory, pairs of virtual particles are constantly popping in and out of existence in the vacuum of space. One particle might fall into the black hole, while the other escapes into space. The escaping particle carries away a tiny bit of the black hole's energy, causing the black hole to slowly lose mass over time. This process is incredibly slow, and for typical black holes, the evaporation time is vastly longer than the current age of the universe. Section 7. Detecting the invisible. Peering into the abyss. Black holes are invisible to telescopes that detect visible light, X-rays, or other forms of electromagnetic radiation. So how do we know they exist? The answer lies in their gravitational influence on their surroundings. One way we detect black holes is by observing the motion of stars and gas clouds orbiting around them. Just like planets orbiting a star, these objects are influenced by the black hole's gravity, allowing us to infer the presence of the unseen object. Another way to detect black holes is by observing the radiation emitted by the material falling into them. As gas and dust spiral towards a black hole, they heat up and emit radiation across the electromagnetic spectrum, from radio waves to X-rays. By studying this radiation, astronomers can learn about the properties of the black hole, such as its mass, spin, and the rate at which it is accreting matter. Section 8. Galactic giants, supermassive black holes. While stellar mass black holes are impressive in their own right, they are dwarfed by the supermassive black holes that lurk at the centers of most galaxies, including our own Milky Way. These cosmic titans can have masses millions or even billions of times greater than our Sun. Supermassive black holes are thought to have played a crucial role in the evolution of galaxies. Their immense gravity can drive the formation of stars and influence the dynamics of entire galaxies. There appears to be a correlation between the mass of a supermassive black hole and the mass of the central bulge of its host galaxy, suggesting a coevolutionary relationship. Section 9. Cosmic influence. The role of black holes in the universe. Black holes, once considered mere curiosities, are now recognized as fundamental players in the cosmic drama. Their influence extends far beyond their immediate surroundings, shaping the evolution of galaxies and influencing the large-scale structure of the universe. Supermassive black holes, in particular, are thought to play a crucial role in galaxy formation and evolution. Their immense gravity can drive the formation of stars and regulate star formation rates by accreting matter and releasing powerful jets of energy. These jets, composed of high-energy particles, can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism between black holes and their host galaxies is thought to be responsible for the observed properties of galaxies today. Section 10. Mind-blowing black hole facts. Black holes are some of the most fascinating and mind-boggling objects in the universe. Here are a few fun facts about these cosmic enigmas. Time slows down near a black hole. Due to the intense gravity near a black hole, time actually slows down relative to observers farther away. This effect, known as time dilation, is a prediction of Einstein's theory of general relativity. Black holes can spaghettify objects. As an object falls towards a black hole, the difference in gravitational pull between its closer and farther sides becomes extreme, stretching the object like spaghetti. This process is known as spaghettification, or the noodle effect. Black holes are not actually black. While black holes themselves do not emit light, the material falling into them can heat up to extremely high temperatures, emitting radiation across the electromagnetic spectrum. This radiation is what allows us to detect and study black holes. Our galaxy has a supermassive black hole at its center. Section 11. Conclusion: unraveling the enigma of black holes. Black holes, once relegated to the realm of science fiction, have emerged as fundamental constituents of our universe. These cosmic abysses, where gravity reigns supreme, continue to captivate our imaginations and challenge our understanding of the cosmos. From their birth in the fiery death throes of massive stars to their potential role in the evolution of galaxies, black holes have revealed themselves to be far more than just cosmic oddities. They are integral components of the cosmic tapestry, influencing the structure and evolution of the universe on grand scales. While we have made significant strides in understanding these enigmatic objects, many mysteries remain. The journey into the abyss has just begun.